We're very grateful and excited to be joined by Philippe Schwaller, who comes to us from the EPFL in Switzerland. Philippe there is an assistant professor, and he leads the Laboratory of Artificial Chemical Intelligence. A very interesting background, chemist with a lot of diverse interdisciplinary training, and it's clear he brings this actually with tremendous insight into all of his research that he's doing. Also spent time 5 years at IBM, research and completed his master's in philosophy or MPhil in physics. So he has a very diverse background, and he brings all of that actually to bear upon the work that he's doing. And Philippe, we're really grateful for you taking the time to join us, and we're looking forward to your talk. Thanks.
Thank you very much for having me. Yes, today I'll be talking about teaching language models to speak chemistry, and I don't think I need that slide. We all know that we have an endless chemical and material space to explore, and if we take drug-like molecules, then the number is estimated to be 10 to the power of 60. My lab at EPFL is thinking about how can we use machine learning to accelerate that chemical design cycle, really from kind of what molecule we want to make with applications in drug discovery and catalysis. Always thinking of experimental validation. We're purely digital lab, so we're covering that with collaborations. But this is typically not done in machine, or not often done. Like I think like your consortium is unique for that because you bring machine learning and chemists together, but like kind of often this lacks in machine learning papers because how to make molecules is actually not a solved problem. And I think Marty like presented super exciting approaches, and yeah. But yeah, we're working on all of that from like really small language models for more de novo molecular design to like large language models applied to chemical research. And today I will focus more on the large language models. But what they all have kind of in common, if we want to use kind of language models in chemistry, we need a text-based representation. And what is kind of impressive is that the SMILES representation that was introduced back in the 80s is actually still used today and fits those language models super well. Here you just have an example. I don't know if you see my pointer, but you have an example of a graph and how it's decomposed here in the SMILES. You have like kind of the brackets for the branching and the numbers for ring openings and closings. And back during my time at the University of Cambridge, I actually like kind of introduced the first transformer model applied to chemistry, and back then it was used for predicting chemical reactions. So learning kind of a translation functions between like precursor molecules and products. And I would say the transform model, which in its decoder form is now used behind like GPT, for example, that you all know from like ChatGPT, is kind of still the workhorse in language models. If we look at kind of language models for chemical synthesis, like a few years back, we were really focusing on single modalities. Like I was explaining to you in the last slide, like translating, for example, from reactants to products for reaction prediction, doing the other way around for retrosynthetic planning, or like kind of trying to predict reaction conditions with language models. Then came a time where we started like combining multiple modalities, like going more towards automation, say, hey, can we like take reactions represented as SMILES and maybe convert them into structured actions that give us recipes that we could then perform in the lab. And more recently, with like all those large language models becoming so popular, we started also using like kind of general purpose models and trying to make them valuable somewhere in chemistry. And today I will kind of focus on this work on ChemCrow, but there are plenty of other examples also by Alana Spur-Guzik or Gabe Gomez that go in the same direction. Just because I'll be talking about large language models and large language model agents, typically when you have a large language model, you have a user query and it will just spit out an answer. And if you are somewhere in chemistry, you're typically getting like they're getting better and better. But you kind of, if you push them too far outside the training distribution, they will just confidently hallucinate something. When you go to large language model agents, you add the ability to take actions, and this can kind of be queries to external tools like querying a database, doing a web search, writing some code, and so on. And kind of with this, it reduces the hallucinations because it can kind of get accurate information from somewhere else. And yeah, for the moment, like still most general purpose large language models lack of chemical knowledge and reasoning and could be much improved. And back even before GPT-4, we kind of started working on making large language models useful for chemistry. And we had observed that, yeah, even, yeah, all the tools we were playing around with were kind of bad at chemistry, but we had those excellent chemistry tools living somewhere in isolation, like kind of one GitHub repo there, another API here, and kind of hard to combine if you're not an expert Python user. So our solution to that was ChemCrow. Crow, because crows are like known to use tools very well. And this is joint work with Andrew White, who is and Sam, who are now at Future House, folks from IBM, and Andres, one of my PhD students. So what tools did we give to ChemCrow? Like we gave it molecular tools to calculate some properties, find similar molecules, check the patterns for novelties, convert them to structural information, some general tools like literature search, web search, code, even the human expert was a tool for the large language model, then some reaction specific tools, and in the end also some safety tools. And given that tool set, the language model would not now not just hallucinate something, but like kind of think about the task in question, select an action which could provide more information, then generate the input to that action tool and get back an accurate, hopefully accurate answer. And given this additional information, again, think about what is now the best action to take to kind of continue to collect information until it can solve the task. The cool thing here, I would say, is that, okay, language is the interface. You're always passing like text and getting back text, but nothing actually prevents you to have a tool that would run a simulation and use the 3D coordinates of a molecule to kind of compute some property, as long as what you're passing back to the model is actually, again, text. And here's just one fun example that we used in automatic synthesis. So plan and execute the synthesis of an insect repellent. And for this, the language model had first to find out what is a common insect repellent, and for this it queried the literature and got back a few options. But if you look at those common names, they do not contain any structural information. So the next tool that it called was the name to smiles to get back the smiles of DEET. And with that, it could then query the synthesis planning tools where the tool performed the retrosynthesis and converted all the synthesis steps into recipes. And in the end, because we connected it to RoboRxN at IBM, after 2 hours, we had DEET confirmed. And this was one of the first examples, if not the first example, like from prompt getting information from different tools to the automated synthesis on a robotic platform. This is just to show you that, like, kind of this platform exists. I don't know if share computer sound off. Yeah, like here you have the sound, but this is the platform at IBM Research. We went on and also worked on some thiourea organocatalysts and let the model kind of predict retrosynthetic paths to them and then perform the reactions on the RoboRxN. And in the future, we're also planning to collaborate with Swisscat Plus at ETH Zurich and EPFL to do more exciting automated workflows with agents. Here you have a graphical user interface that Andres programmed at some point, and this is freely available. The open source version does not have all the tools to connect to RoboRxN, but most of the tools are there, and kind of the overall workflow can be taken from that. It's modular, and really kind of worked on that before GPT-4 was published. GPT-4 unlocked a few additional kind of use cases, but now, two years later, we would kind of certainly change the LLM to something more open, change the tool set, everything, like kind of you can really kind of make the tool set targeted for your specific use case. Also, like this was back in 2023, the GPT-4 model. This is just one of the standard benchmarks in natural language understanding. And what you can see between like closed source and open models, like kind of the gap is closing a little bit. And also models are getting smaller for the same performance. And at some point, I'm sure that even chemistry will have like very capable models that can be run on reasonable hardware. Automated synthesis, I think, is not far from being solved because, like, while we show you this, or while I show you the successes here, like, kind of as soon as you involve kind of a robotic platform, and I'm sure you know that better than I do, like, kind of you get a lot of challenges more on the engineering side, and kind of you can also just work with all the components that you have available at that specific point in time in the robotic platform. And I would say, at least for like more challenge, no, but like for some kind of molecules, the synthesis planning models are still weak. While they suggest sometimes very good synthesis routes, it's kind of like a lot of the synthesis routes that are predicted still have some obvious mistakes inside. And yeah, there needs to be more thinking about how we can kind of filter out the crap before showing them to a chemist or trying to automate the synthesis directly. And whenever I try to talk to my friends in organic chemistry, what they would be more excited about is like synthesis to compounds or to natural products like vitamin B12, and not the simple stuff that we can typically predict with those models. But I'm currently working with Daniel and Slatko on more strategic synthesis planning models. In any case, to kind of make progress, I think we need proper benchmarks. Like kind of one of the biggest challenges that we had with ChemCrow was really like, how do you benchmark now not kind of a regression or classification model or just a reaction prediction model where you can kind of compare with the ground truth like major product. But how do you like benchmark workflows, or how do you benchmark LLMs in chemistry? And this is when I teamed up with Kevin Jablonka, and we developed ChemBench, which is a multiple choice question answering data set with 2,700 questions in chemistry across different topics. And what we see is that kind of the most recent models are actually quite good. At least the closed source one. The open source ones still need a bit to catch up, but compared to human experts that we had like 19 humans that kind of more or less at PhD level that kind of answered plenty of those questions, and compared to them, like the language models performed quite well. But the question is always, is multiple choice like really correlating with what we are actually interested in getting from those large language models? So is a large language model that is good at answering those questions, which is often like learning by heart some facts, really also good at solving some problems we are actually kind of caring about. And for that, like kind of, we recently worked in my group on like kind of using them slightly differently, because we observed that, okay, we can fine tune them from property prediction, and they're reasonably good in the agentic workflows and multiple choice questions. But as soon as we kind of push them to generate, like, I don't know, even just to predict chemical reactions for which you can train a molecular transformer in a single day on one GPU, anyone can nearly, you could even do it in the Google Colab, I guess. So and it reaches 90%, and then LLM fine-tuned on the same task is far away from that. We kind of said like maybe we have to do something else. And what we've realized quickly is that they were actually, if you show large language models chemical reactions described as smiles, for example, they are very good at analyzing what is actually happening in the chemical reaction. They're just not very good at kind of generating the whole smiles. So we use that to kind of our advantage, and we kind of use more traditional search algorithms to come up with plenty of diverse solutions, for example, for synthesis paths, and then kind of used this natural language interface to like give the overall pipeline some additional constraints, like kind of expert queries describing the reactions that should happen where, disconnections, strategic patterns, and so on. And we used the LLM then to score the alignment between all the suggestions and the actual user query. And if we do that for synthesis planning, for example, we can kind of a large language model is able to analyze like a synthesis route of 15 or 20 steps, and then using a natural language query is able to kind of give it a score how well the suggestion actually kind of aligns with that query. And for this, we developed a new benchmark, and we see that particularly like the Claude models and also DeepSeek perform reasonably well on like analyzing whole synthesis routes. I think this is kind of super exciting because this is just an interface to a retrosynthesis tool we are currently developing, and you can kind of now get a lot of suggestions, which you can get from any, like you can use AI SynFinder, for example, from AstraZeneca, but like there's the problem that typically the top rated routes do not align with what you have in mind. So now you can have a steering prompt and you have like an analysis by the LLM that goes through every reaction and kind of describes it and assess how well it aligns with what you actually want to see. And so this is a way to really go to steerable synthesis planning and kind of we can this is just the other way around where we kind of look for an early ring formation and we can find routes that align very well with through the LLM, and we could just re-rank them by the LLM score and actually easily find in all those suggestions what could be nice ideas for the actual route we care about. And because it's natural language, you can really query for most of the things that come to your mind. We tested that on the super large scale, like up to 26-step synthesis, but you can do the exact same thing also on reaction mechanism elucidation, and kind of there we built a small benchmarks where we kind of encoded the elementary steps and gave the LLM like different options, like good ones and bad ones, to rank. And also there we see similar trends where Claude 3.7 Sonnet performs quite well. And we also tried, at least at the beginning, to help the model to kind of, with a description of the actual reaction that we are expecting, a general description, but those expert prompt for the best models do not kind of help that much anymore. Yeah. In the end, those are all kind of digital benchmarks, and what we really kind of what we should really aim for is kind of experimental validation. And we're doing that, but my lab exists since 3 years, so kind of it takes time. Like one example where we actually achieved experimental validation is with Bojana and a collaboration with the Monsanti lab at EPFL, and there we kind of wanted to use machine learning to link the synthesis of a copper nanocrystal to its outcome. And as a proxy for reactivity, we looked for synthesizing copper nanocrystal with a particular shape. Luckily, there was the speaker just before me that well introduced Bayesian optimization. But in that work, we not only kind of looked at like how we can integrate Bayesian optimization in the lab, but we helped that lab to actually like move everything to electronic lab notebooks, like automatically connect to those notebooks and kind of build this into the Bayesian optimization loop. And if you imagine shapes, then kind of the challenge there is that you're now not optimizing for typically not optimizing for typical value, but like those are categories. So we had to come up with a trick to be able to optimize for shapes that were not yet observed in the training data. And we tested our approach where we were using a surface energy scale for the different shapes that could exist on first on cubes, where we kind of removed all the known cube synthesis from the training set. And then over a few iterations, we were actually, by targeting the specific surface energy value in our optimization, able to get cubes in the synthesis. What is kind of challenging in this whole more material space is that there you have plenty of different syntheses that lead to the same outcome. And if you look at this black line here, this is the synthesis that we found to like synthesize cubes, and it looks nothing like the synthesis parameters that were previously reported in literature, and same for tetrahedral. But those shapes were all known, so this is not super exciting. So basically what we did next is kind of to target a shape, rhombic dodecahedral, which was kind of only reported for gold, for example, but never previously reported for copper. And there again, like kind of in the third iteration, we observed the first time rhombic dodecahedral, but kind of it was like a very mixed sample with plenty of different shapes. So at that point, we decided to also not only optimize for this energy scale, but also for the peaks in the XRD. And like that, over 9 iterations, we got to a perfectly pure sample. But all that work kind of motivated another study, because in my AI for chemistry course, in like kind of every time I talk about Bayesian optimization, like kind of when a new person comes in and says, I would like to apply like kind of Bayesian optimization to my my reaction, how should we featureize this kind of, how should we featureize that reaction? Should we kind of calculate some DFT descriptors on the ligands and the catalyst, or what should we do? And this is kind of, we always get stuck there because you kind of need already a few data points if you want to validate the featureization and so on. So we thought about, could we maybe get to a more holistic featureization? And 1.5 years ago, we kind of thought like, okay, why not try to use LLMs? We can just encode anything with LLMs. So why not try to use LLMs to feature the synthesis procedure directly, or like kind of the chemical reaction conditions or whatever you want. But compared to like domain-specific representations, which you have here on the left, just a fixed LLM embedding was not informative enough, and it was general but underperforming. So that's why we recently developed, we released a preprint last week, an approach where we can jointly train an LLM through parameter efficient fine tuning and through the Gaussian process loss, and kind of basically backpropagate also through the LLM, and with very limited amount of data. Typically, our experiments were like 10 initial data points and 50 iterations, like 50 of batch size 1, we were able to fine tune the LLMs and get better representation. Yeah, this is maybe a bit too much information at once. Those are new slides that I just got from Bojana, and it's kind of the first time I'm including them. So, but what you can see here is kind of at the beginning, you have a latent space that is not ideal here, and kind of during the optimization, it kind of splits like low and high yielding regions. Maybe it's more visible here, where you have the initial embedding, how the space is structured, and even after a few iterations, it can kind of like find out what the high yielding and low yielding points are. I think I'm already over time. I have no measure of time on this single screen, so I really don't know where I'm at the moment. But I can conclude in the next 2 minutes. Yeah, what we see with this joint training with GP and LLM is that we get high predictive accuracy and at the same time well calibrated uncertainty. So basically the model knows which point is certain about and which points it is not. And this is super helpful for optimization. Yeah, I can skip over that, but it's kind of the first joint training of LLMs and GPs. And robust to kind of the input formatting. You can use SMICE or like simplified procedures. It works across encoder decoder models, encoder only models, decode only models, different types of pre-training. We have one single set of hyperparameters that was optimized on one data set, and we kind of show super nice performance on 19 chemistry related data sets. And yeah, I think like kind of this is future like research will probably be somewhere around LLM agent centered research systems, as we've already seen from Marty. And yeah, I think like kind of this is also something my lab is thinking about. But I guess we have to have the benchmarks to kind of develop those systems and use the LLMs where they make sense. And with this, I think like really those LLM-powered agents have the potential to lower the access to plenty of different tools. ChemCrow was one of the first evaluation and like on plenty of generic tasks, but benchmarking is super challenging. We've shown some progress with harder benchmarks on mechanisms and retrosynthesis, and whenever we collaborate with experimentalists, Bayesian optimization is typically kind of a good starting point. And with this, I'd like to thank my whole team and also all the nice funding I get to work on those exciting projects. Thank you very much for your time. I'm sorry to have taken longer than expected.
Oh, awesome. Philippe, thanks. That was fantastic.
A
Thank
little
you
bit
so
more
much.
slides than, yeah. Yes.
All right.
Yeah.
So, okay, great. So we're open for questions.
Yeah.
Yeah, thank you for your great talk. You mentioned that you ordered multiple outputs for NLM for better prediction. Would you explain how you ordered multiple outputs to user's query? Did you calculate embedding subtext and similarity to user's query?
Can you just repeat the question?
Yeah, you said you ordered multiple LLM outputs for synthesis prediction during your talk. So I wonder how you ordered multiple LLM outputs to user's query. What similarity you calculated to order the outputs?
Okay, no, it's basically, no, it's like every single for example, in retrosynthesis, every single reaction gets a small description by the LLM and then an overall assessment how it aligns to the user query. So like kind of the LLM reasons really reaction by reaction, and then is strong enough to see whether like what it describes along the synthesis actually aligns with whether a specific ring formation happens at the start or not, whether like some building blocks are obtained from commercially, whether some rings are from commercially available building blocks or not. Like kind of, you can ask it whatever you want to see in the strategy. And the LLM, the score comes from the LLM itself. We just prompt it to give a score, alignment score from 1 to 10. And using that, we reorder the synthesis suggestions.
Okay, thank you.
Great. Dee from the front.
Hey, thank you for the talk. So regarding molecule representation, outside of smiles and selfies, have you ever looked into like graph neural networks? Would that be practical to apply for the models?
I think like kind of, graph neural networks or diffusion models, you can, there are plenty of representations that work well. Like kind of, it's really like I have a sub team in my group that also works a lot with diffusion models, more in the drug discovery space. I think like kind of I'm model agnostic, but because it was, I think like the request for that talk was more about agents. I showed you more the stuff that we do with language. I think like so far I had more success with smiles versus selfies. I don't know why. Like kind of maybe because at least in language models or like on the internet, you will definitely find more smiles than selfies, and they might have learned this representation at some point. But for large language models, you can even use IUPAC names, and you typically get the same. And if you fine tune them through a GP with like 60 data points, you don't care about the representation. Whatever you give it, it will learn it from the data. Yeah.
Got it. Thank you.
Okay, if there are no more questions, please join me in thanking Philippe for a really nice talk.